Hey, welcome back. We're in day 2 of section 4.7. We're continuing to look at some applied optimization problems. Just like in day 1, I'm going to keep this one example per video, trying to keep the video less than 10 minutes so you can focus on them. Last time in the first day, I focused on problems that were mainly about distance. There was some kind of just mathematics problems to warm us up about products and sums. In this one, we're going to look at some problems that have a little bit more geometric flavor, some things that involve shapes, trying to remind you what I mean by things being inscribed and other things, volumes, surface areas of three-dimensional objects, and then maybe an example that has something to do with time. All right, so those are just kind of the subject matters of this second day. It's really the same material in section 4.7. It's all about trying to identify an objective function and find its minimums or maximum values. Okay, so let's take a look at the example that I've chosen to look at first with you guys. I want to find the area of the largest rectangle that can be inscribed in a semicircle with radius r. All right, so there's a lot to unpack here. I'll never make these things very realistic in terms of how quickly I go through them, but I'm asking find the largest area. So my objective function is going to be some area. If we start trying to pick this thing apart, right, I want the area. That's my objective function. I want it to be as big as possible. And then, I know what a rectangle is, but this rectangle has to be inscribed. I want to talk a little bit about what that means in a semicircle, and the semicircle doesn't have a specified radius, although it is a constant. Okay, so it doesn't change in the problem. Let's click over to a little animation that I made for you. You're looking at a picture of a rectangle that's inscribed in a semicircle. So you've got the semicircle drawn here in green. I've got it centered at the origin in an XY coordinate system. So to say that a rectangle is inscribed in a semicircle, it means that one of the side lengths of the rectangle is along the diameter of the circle, and then the two vertices that aren't on that side length are on the circle. Okay, so this is a picture of an inscribed rectangle. So it's one side length is along a diameter of the semicircle. The 2 points that aren't on that side length are on the circle. And we want to find the area of the largest rectangle. So I want to try to understand that problem. Like, well, what does that mean? I mean, here I've got a rectangle inscribed in a semicircle. It has some area. And I can see if I move the slider, there are other rectangles. I'm not calculating the area as I go, but in this rectangle that I just moved the slider to, I've decreased the height, yeah? Decreasing the height of a rectangle in general, if nothing else changes, will decrease its area. But you saw when I moved the slider that the length of the rectangle, or the width, if you like to call it in this picture, it also increased. So the increasing width makes the area want to get a little bit bigger. But I can see if I kind of go towards extremes, like this rectangle, its height, I went so far, its height is getting so small that the area of that rectangle is going to be tiny. In fact, when I let x get to the edge of the circle, it's 0. It's kind of a degenerate inscribed rectangle. It has area 0. But if I start moving the points of where I'm inscribing back, then the areas got bigger. And they're getting bigger, maybe, I don't know. Now I can see that they're definitely going to be getting smaller because now the width is approaching 0. Yeah, so here's kind of the other degenerate case when the 2 points coincide at the top. So of all those areas in between, one of them had to be biggest. And that's what the question is. How big is it? How big can you make the area of this rectangle if we're going to keep it inscribed in this semicircle? All right. So that's just a useful, you can draw a bunch of pictures like that. You don't have to animate it on a screen, but it's an important first step in any one of these problems is, like the author says, you have to understand the problem. What is the mathematics problem that we're trying to solve here? All right, so let's switch back to the whiteboard and see if we can't go about coordinatizing this problem and writing down the objective function as a function of some variable, and then try to maximize that function. All right, so I've got our kind of animation picture brought here, and I'm going to, again, to kind of make these shorter, I've written out all the computations. I'll just try to walk you through them, but I would advise you as you're watching this video, anytime I'm computing a derivative or solving an equation, stop the video and compute that derivative and solve that equation yourself. See if you get the same thing I do, and if you don't, kind of try to ask yourself what went wrong. All right, so here we've got our picture, and what have I done here? I'm labeling the x coordinate of one of the points of the inscribed rectangle with a variable x. Because once you choose that variable x, well, you're basically determining where this corner of the rectangle is because it has to be on the curve. And because this thing's inscribed, once you pick one corner of the rectangle, the entire rectangle is determined. All right, so the value of that variable determines the whole rectangle. I've labeled the coordinates of that point in the upper right-hand corner, x, comma, well, square root of r squared minus x squared, because that is the equation of that upper semicircle. Yeah, you might remember that the equation of a circle with center 0, 0, and radius r in the Cartesian coordinate system is given by x squared plus y squared is equal to r squared, right? So this is a circle. Its center is 0, 0. Its radius is r. And basically, I just solved that equation for y, taking the positive square root to get this upper semicircle. All right, so that's how I know that the y coordinate of the point whose x coordinate is x is given by the square root of r squared minus x squared. Okay, well, the area of a rectangle is certainly its width times its height. Yeah, the area of a rectangle, you multiply its width by its height. The width in this picture, you can see, well, the whole rectangle has width 2x. Yeah, the width down there is 2x because, well, the measurement x itself is how far you are from the origin to this point. But by symmetry, this other line segment is that exact same length. So that's why I'm doubling it. Okay, the height of the rectangle, well, that's the y coordinate there in that picture. Yeah, so the height of the rectangle is this square root term. Its height is how far you are from the x-axis. That's the y value. That's the square root of r squared minus x squared. So their product, 2x times that square root, is our area. And this problem has a finite domain. Yeah, the biggest value, or excuse me, the smallest value that x can be is 0. That's when we got that degenerate rectangle that was width 0 and height r. So it has area 0. But x certainly can't exceed r because we have to keep this thing in the rectangle. So if you make x equal to r, that was the degenerate case where the rectangle's height went to 0 and its width was 2r. All right, so we don't have to use the first derivative test. We can use material, or the theory rather, from section 4.1. We've got a function and we want to optimize it on a closed interval. So you remember from section 4.1 what we're going to do. We're going to find any and all critical points of that function in that interval, and we're going to make a table of those critical points together with these two endpoints. And we'll be able to see the largest output of our function in that table. All right, for differentiation purposes, I'm just rewriting a here. Instead of that square root, I'm writing it as a 1/2 power. And now it's time to take the derivative of a to find any critical points that are in our interval. What's going to be involved in taking the derivative of a? Well, there's going to be a little product rule, because we have 2x times something, and then this square root term is going to involve the chain rule, because it's the square root of r squared minus x squared. All right, so let's look at the computation. Stop the video and do it yourself. Perfect chance right now. Stop this video and compute the derivative of a and simplify it as much as you can. Then you can start the video back up and see if you get the same thing that I'm about to write down. So I won't unveil the computation one line at a time. Let's just look at it. So what did I do? I'm taking the derivative of a. I'm using the product rule. All right. So the derivative of 2x is 2. And then I've got the other factor undifferentiated. And now plus the 2x undifferentiated, and now I'm differentiating that square root term. Okay, the derivative of a square root is 1/2 whatever's in it to the minus 1/2 times, the chain rule says, the derivative of what's in it, that's negative 2x. So there the calculus is done in that line, no more calculus. And now I'm doing some algebra. So I'll kind of explain what I'm doing here. Maybe I can underline. I've got r squared minus x squared to the power minus 1/2, and I've got it to the power 1/2 in those two terms. So you can always factor out the smaller power. Yeah, when you have some quantity in more than one term of an expression, you can factor out the smallest power of that quantity. So I'm factoring out r squared minus x squared to the minus 1/2. So what would be left? Well, in this first term, I would have to have the exponent 1/2 minus a minus 1/2. That's a 1. So when you factor r squared minus x squared to the minus 1/2 out of this first term, you're left with 2 times r squared minus x squared to the first power. Out of this term, it's completely gone because you factored it out. So what would be left? Well, the 2 times the half cancels. I can show you that. And then what else is here? I've got a -2 and an x and an x. That's where that -2x squared came from. All right. I'll let you check that if you distribute that 2 through there and combine like terms, and I factored a 2 out, the numerator simplifies to 2 times the quantity r squared minus 2x squared. The denominator is, I wrote this as a positive power, so it's r squared minus x squared to the plus 1/2 downstairs. Okay. So now critical points, looking at that derivative. The derivative is undefined when the denominator is 0. The only value that makes that denominator 0 is r. R squared minus x squared is 0 if and only if x is plus or minus r and our x is positive. So we'd have to take x to be r, right? So that's a critical point. It also happens to be an endpoint. Good. You don't have to list it in the table twice. How can the derivative be 0? A fraction is 0 if and only if its numerator is. Yeah, so the numerator of that fraction is 0 if and only if r squared minus 2x squared is 0. If you solve that for x, you get plus or minus r over the square root of 2. We're going to discount the negative one because our x, again, is between 0 and 2. So we get one critical point. So if we take a look at that information in a table, what have I got listed in my table? I got my two endpoints, 0 and r. And then I've got the one and only one critical point in the interval that we're looking at, r over the square root of 2. Negative r over the square root of 2 is not in the interval of consideration. I rewrote the function a here just for convenience. And now again, stop the video, you do these evaluations. If you plug in 0 for x, you're going to get 0. That was that degenerate rectangle. We saw that. It had no width. If you plug in r for x, you're going to get 2 times r minus or times 0. That's also 0. That's the degenerate rectangle that had no height. Okay? And then if you plug in the square root of, or sorry, r over the square root of 2, well, that goes right here. That you square that, you get r squared over 2. Subtract that from r squared, and you get r squared over 2. So in other words, you'd end up getting 2 times the square root of, or r over the square root of 2 times r over the square root of 2 again. And that all simplifies out to r squared. And that's clearly the maximum value. It wasn't stated in the problem, but I'm assuming that r is positive, so r squared is bigger than 0. All right, so we don't have to use the first derivative test. This was on a closed interval. We can just state our answer. I'm going to end this video with a nice clean statement of my answer and as a complete sentence. The area of the largest rectangle that can be inscribed in a semicircle of radius r is r squared. All right, so I hope you liked that example, and I'll make a couple of more. Thanks for listening.